I think everyone here knows me, right, or seen me talk or whatnot. I'm actually really thrilled that there's so many people here because a lot of people were leaving LISA last night and weren't staying the full day. So being at the end of Friday is always it's a risky thing because you end up with a small room and whatnot. But I'm super thrilled you're all here, and hopefully you'll all be at closing as well. So here we are. We're going to talk about data visualization. Now this started out as a metrics dashboardy type thing, but then I started getting into the psychology of visualization and how human perception works, and I found that was way more interesting stuff. While I didn't make the slides until mostly today, the actual talk itself has been in my head for about 9 months, so hopefully it'll all work out. First off, if you want to take a picture of a slide, this is the one to take a picture of, because if you go and read all this stuff, then it's the same as if you just listen to my talk. But if you're here listening to the talk, then you don't need to take a picture of the slide. So anyway, these are all great resources. Everyone here, who here has heard of and read Tufte? Who's heard of Tufte? Everyone. Who's actually read it cover to cover? Yes, these are my people. These are the data nerds, all right? The rest of these are further back research into all this. You notice that several of them are dated from the 60s and the 50s. That's because people have been thinking about this stuff for a long time. And then there's the psychology of data presentation, all this stuff. But let's get into what visualization is. When we try and visualize data, we do this wonderful and somewhat dumb thing where we take numbers, we turn them into pictures, and then we give a human being the task of, in their mind, undoing the picturification of the numbers to get back to the numbers that we put in the picture in the first place. And it seems like a really silly exercise. But the reality is, because there are usually so many numbers, we often want to tell a story about what's in the data or find something interesting, and visualizations allow us to use our very, very powerful visual processing capabilities that humans have to find interesting patterns and see things that are cool. The problem is that human beings really suck about just about everything. Ultimately, a human being is a brain on top of a wobbly bag of meat that has evolved to basically try and keep that wobbly bag of meat from falling over, being injured, or something else. And that's about all that brain is good for. However, in the process of becoming that brain with a wobbly bag of meat, there were certain capabilities that we developed internally. First is memory, which is our ability to, to recall information and apply it over time, learning and so on. And there are three basic kinds of information. There's iconic memory, which we really have very little control over. This is something that it's built into how our brain quickly processes information during the pre-attentive phase of thought. All right, when we sit and think about something, you can sit and ponder the meaning of life and whatnot, but when someone throws a baseball at you really, really fast, or a tiger leaps out at you really, really fast, are people tweeting me? Oh my God, okay, I forgot to silence my phone, I'm sorry. Oh, good, okay. Yeah, I actually powered it off because I got a system update and now none of my apps work. Which was great when I was tethered at 1 o'clock trying to finish my slides and tethering wasn't working. Okay, so the pre-attentive part of thought is the pre-processing. It's like the C++ preprocessor. It basically bakes the data a little bit before your type 1 or type 2 thought process kicks in. Type 1 is your instinctual thought process, like if you, where you don't really think why you're doing something, you just do it. It's like when someone puts a bowl of potato chips next to you, you might just casually, and you don't even, hey, I'm eating potato chips, right? Because that's type 1 thought. It's like, hey, there's potato chips. Part of my brain saw potato chips. I like potato chips. I'm gonna eat these potato chips, right? That's type 1 thought. Type 2 is the part that kicks in when we're doing our hardest part of our jobs, and usually the most interesting part of our jobs. When we're doing on-call response, when we're actually trying to work a really meaty problem where we have to engage all of our cognitive faculties. And it's also the part that every time someone taps us on the shoulder or sends us an IM, it completely disrupts it, because type 2 thought, that deliberative thought, takes a long time to spin up to get engaged because it requires so much of your mental capacity. But the good news is most of our world is type 1 thought. We're purely reactive, and it's the type of thought that keeps us alive and has kept that brain on the wobbly bag of meat from dying for so many years. Okay? And then there's memory. They got short-term and long-term. These are different types of access memory. All of these things come into play when we examine visualizations of data. And we can manipulate all of these things to create different stories with data, because people will read information in different ways. Most of what screws up graphs happens in the pre-attentive thought phase. Now, this is where our brain automatically will recognize how big or small something is, relative sizes. It'll recognize where things are in relation to each other. It recognizes things like the color, the intensity of the color. It recognizes whether things are grouped in through what's called enclosure, where they are in a box together or some other visual containment. It also can count up to about 4. You don't actually need to count most things. If I threw between 1 and 5 marbles on the floor and you glanced at it, before you even thought how many there were, you already know how many there are because you can count up to 4 in real time without any actual type 1 or type 2 thought process. It also does grouping, and this is broken out into a lot of different categories of grouping because the grouping part of your pre-attentive thought, before you even begin thinking about what you're looking at, it has already merged parts of it into unique collections that help the type 1 or type 2 thought process then further extrapolate, okay, these things are related and I'm going to think about them as a combined whole as opposed to 9 different elements. Here's a great example. It's a classic example where as the moment this slide came up, you all immediately knew there were 4 items. You didn't have to go 1, 2, 3, damn. Well, some of us have to take our shoes off to count everything that we see. What? 2 exclamation points, yeah. It does look like 2 exclamation points. See, now there, that actually starts getting into iconic memory. And interestingly enough, when I was putting this example up, your pre-attentive attention has counted 4 elements, and it may have, this is a very weak association, done a shape association. All right, they're a little bit far apart, but you might have also mentally subgrouped them into 2 squares and 2 circles. Now, when I first created this diagram, if you invert this diagram vertically where it's circles on top of squares, a different type of pre-attentive recognition kicks in because they look like little bodies, little head on top of a torso, and you group them horizontally into 2 side-by-side things. But if you flip it, it completely cancels out that mental effect, and instead you may get a weak shape-based orientation. But this is how the pre-attentive brains already combine this data together. Now, connection is a very, very strong association. Unlike proximity or shape, when you connect these things together, your brain counted to 2 here and it stopped at 2. It's only by applying type 1 or type 2 thought you then say, wait, no, there are also 1, 2, 3, 4 shapes there because in your brain, in the pre-attentive phase, it said it stopped at 2 because these were connected, right? You don't count the lion's head and its feet and its torso and its tail separately. It's a lion. That's the most important thing about recognizing the lion is that there's a whole lion there, right? Those who did not think that, not around anymore, right? So hopefully not a lot of us encounter lions in our day-to-day lives, but I think you get my point that this is how our brains are wired because it serves an advantage. Similarly, size. When I do this, now here this creates confusion because both size and shape are weaker than connection, right? And so some people might, if we were to survey the room and say which of these 2 more naturally goes together, some people might say the small ones go together, the small ones and the big ones go together, or some people might say the squares go together and the circles go together. But as soon as I throw in a connection of some kind, then it's obvious everyone will agree on how to group these things together because there's only 2 objects left. Of course, then you start doing something like this, and there you might begin tripping over where pre-attentive and type 1 thought breaks and is like, this doesn't, okay, there's a scale. These are entire objects that are scaled with relation to each other, so there's still 2 objects. But you see how all of these different binning mechanisms add up to some weighted value in your brain, and it's all automatic, and it's a beautiful aspect of how the human brain works. Beautiful to a degree. Proximity. Now here, there are still 4 objects, but because of the drastically exaggerated proximity to each other, most people will count 2. There are 2 groups, right? Yeah, there are still 4 objects, but the association between the separation of them and the tight closeness between them, you have proximity creating an affinity, and so people will equally say there are 4 or there are 2 things on this screen. Now, the interesting thing about proximity is it fails in fun ways. These 4 objects have the exact same relative spacing when in the grouping dimension. They are vertically about 20% closer together than they are horizontally. But we don't see that. And that's because over long distance, grouping begins to fail. Because part of what makes grouping is when something's close together, it's grouped. When it's far apart, it's not grouped, right? But so in here, we can't actually perceive very well that that the squares and the circles are about 20% closer together than the squares and squares or the circles and circles, right? So this gets us to long distance. This is the first place where charts can begin to fail us, when graphs can begin to fail us. Because one of the most popular ways of charting things is bar charts, right? All right, I got 2 bars here on my bar chart. Now, if someone is dealing with someone, if someone has a coworker that likes to make 3D stacked, wonderful, complex, multidimensional bar charts, you'll often end up in a situation where the 2 things you're trying to compare are not, I want to say visually coplanar, you know, in the sense that there appears to be a depth relationship or something. And so the question is, which of these bars is longer, or are they the same? Right? If one is revenue, or if one is error rate yesterday and one's error rate today, do we need to be concerned, unconcerned, or happy? Is error rates going down, right? It's almost impossible to tell. Now, there are techniques you can use when doing graphing, like adding a bounding box that provides constant reference. Now, in this case, because the outer white outline is the exact same height on both of them, we can infer, but we're doing a type 1 inference. We've completely left the world of pre-attentive thought. Now we have to sit and think about this graph, and we either do a type 1 or type 2 analysis. Okay, if the overall outline is the same size and the white box is half the size on B than it is at A, then B must be a little bit bigger than A, right? And you might not believe me looking at this. In fact, I stared at this for a long time, and I actually had to sit down and draw some lines. And indeed, A on the left is the same height as A on the right, and B on the left is the same height as B on the right. But of course, I could be lying about the height of the white boxes, right? And in fact, I could get away with that lie right now, and no one would be the wiser. But because I want to be a trustworthy individual, I'm going to add a few more lines here, which show that the distance, the parallel distance, those are parallel lines. I used copy and paste to create them. Again, you have to have some trust in me here. But the distance between the outermost parallel line and the innermost, the topmost orange line and the bottommost orange line, those are 2 parallel lines, and indeed, if they pass through the same relative points, then by the property of geometry's translation, they are the same height object, right? Because height does not change through translation in geometry. Everyone remembers geometry, right? Translation, rotation do not change any of the relative sizes or lengths of components. Right? But this is interesting though, because these lines are diagonal, right? And there's now the horizontal ones we can get. Okay, the horizontal ones are horizontal and they look parallel, but all of a sudden I'm showing you slanted lines, yet we don't seem to have any difficulty agreeing, or at least coming to a reasonable consensus that those are all parallel. The brain is really weird when it comes to parallel lines. As we begin twisting lines around in different directions, we can still draw parallel conclusions, which is awesome, right? All right, who thinks it's a trick question? Yeah, you guys are on to me. Okay. Well, that's partly true, and we're going to see that right after we talk about angles, because I want to talk about angles before we talk about parallel lines. So angles are a funny thing. Here are 4 angles, all right? They are shown in 4 different orientations, and they're all the same size, right? Approximately? No, that was a trick question. They're all different. Every single one of those angles is different by a slightly different amount. But interestingly, when it comes to acute angles, the human brain almost always underestimates the size of the acute angle. So if you throw up, is this 30 degrees? You'd be like, it looks more like 28 and a half, right? But when presented angle after angle after angle, the human brain for an acute angle will tend to underestimate that. But the weird thing is, if this was all the same angle, these only differ by a few degrees each. If this was the exact same angle, for horizontally represented, the ones on the left and the ones on the right, people will estimate them to be bigger. The error will be on the side of bigger angles, even though they'll still be estimated to be smaller than they actually are. But they'll be even more smaller on the vertical ones. For some reason, we think that vertical angles tend to be smaller than horizontal angles. Again, the brain just can't handle rotation of angles in any way, shape, and form. And those that have talked to me for any length of time about graphs will know where I'm going with when they start talking about rotating angles and comparing values. The rest of you will have to wait. All right, obtuse angles. So that only applies to acute angles. Guess what? When it comes to obtuse angles, we do the exact opposite. We overestimate obtuse angles. So if you were faced with a graph that had various angles plotted on it, and you were asked to say, what would you estimate the absolute value of them, or compare them and try and rank them, could you sort this set of obtuse angles in rank order? I couldn't, right? But they're all slightly different, just like the other one. So obtuse angles tend to be overestimated, acute angles tend to be underestimated. And if you can imagine there might be a charting mechanism that takes advantage of angles, this should be prima facie evidence that you should not be using angles, right? The classic example I like to use to say why such curvilinear graphical representations of things are bad is this one, right? Everyone's seen this visual illusion. It takes advantage of the way our pre-attentive thought process tries to compare these two objects. Already it knows it's got two objects, but the pre-attentive process goes through additional layers of processing. It wants to try and apply that size comparison. But when it tries to apply size, it needs clues that are in proximity to each other. Now the closest edge of the blue arc the closest edge of the blue arc to the red arc is smaller than the arc on the red one. So we begin to think that the red one must be somehow bigger, even though if we apply type 2 thought, we could try and reason otherwise. And if we start drawing lines, it'll turn out that both of these are exactly the same size. But the pre-attentive memory, which has heavy influence on how things feel to us, our instinctive response says, oh, the blue shape's smaller, right? Because our type 1 brain will believe that that's smaller until we engage our type 2 brain and actually start working out the details and say, wait, no, I can see why I might think that because that line there next to the red thing is a small line, but if I look past that line to the one that's way over there, and meanwhile the pre-attentive memory, attention's gotten bored and it's off and it's doing its own thing, and you're like, wait, is there a line around? Okay, I'm cool, go back to work, all right? So pre-attentive memory can be exploited in lots of cool ways for visual illusions because of its desire to create these associations. Cool water. So this is another classic example. Who here has seen this before? Oh, wow. Oh, I'm so excited. Okay. All right. All right. Those of you who've seen this, shh. Okay. So this is a classic example of the pre-attentive's mental process trying to judge hue. Trying to judge gray differences of darkness, right? Because hue, color, is one thing it judges. It judges degree of darkness separately. It's a separate function of the pre-attentive thing, and you place two values on it. And again, color space theory, that's its own whole thing and whatnot. But so when we look at this picture of a checkerboard with a cylinder on it and so on, and there's two tiles, A and B, which one's darker? Someone yell. A looks darker, all right? Which one's lighter? It's B? It's not, no, you know this. No, A and B are the exact same color. They really, 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 really are. I'll leave it as an exercise for you to go and look up the checkerboard gray visual illusion. Don't do it right now, all right? But if you go and you take your hands or you cut a piece of paper out so that it covers everything but just the A and the B, I did that. In fact, as I cut and paste this into my presentation in the bar, I was doing this to make sure I'd gotten a real, because there's some bad versions of this illusion out there. I actually was doing that. And yeah, A and B are the exact same color, but the pre-processing portion of your brain, it uses environmental clues, just like with the size, where it says, okay, I need to know how big this line is. I'm going to look at the thing next to it and see if it's bigger or smaller. It also uses contextual clues to say, oh, B is clearly darker than the squares around it. There's a light square between it and the square that's by A, so A must be darker than B. And it's so hard to break that because the impetus from your pre-processing mental process overrides your type 1 thinking, and you cannot see it. You look at it and you can't see it. You'll cover it up and it's like, oh yeah, they're the same color. Unlike some optical illusions, the moment you uncover it, it goes right back to looking lighter. So anyway, the brain's a wacky thing. Yeah, back to graphics. Perpendicular distance. We were talking about that a little bit ago when I put up this, right? Like how come we can tell that those orange lines appear to be perpendicular when they're slanted, when we just went through the fact that we can't tell angles apart? Well, that's because we're not trying to compare the angle. We aren't saying, okay, we don't look at that and say, is the angle of the orange line and its incidence with the green line the same at those various levels? In fact, the green lines could be gone entirely. Just the lines by themselves we recognize as parallel. This can bite us, though, because let's look at this graph. All right, this is some business process. Could be latency versus incoming request rate or something like that. And we're looking like, oh, we're beginning to asymptote there, aren't we? I mean, does this not look like an asymptote where those two values are converging? Don't overthink it. I mean, I know that I'm tricking, I know that I'm asking you the wrong question every single time, but just be like, yeah, that kind of looks like those things are approaching. Clearly over there at 1, they're very far apart, and over at 10, they have gotten really close together. Well, that's because our brain loves parallel distance. It's trying to create parallel sets of lines, and indeed, the parallel distance between those two things is different. It's much bigger at the bottom than at the top. But remember, this is data. This is something that isn't, you're not going to find a chart in the wilderness being presented to you by a tiger that says, evaluate this graph and I will eat or not eat you, right? This is purely a modern first world problem. That'd be a very weird tiger, but all right, I can imagine a universe in which such tiger exists, but it's implausible in the universe we have available to us at this time. And indeed, again, with cut and paste, that little red line, that's the exact same red line pasted over and over and over and over again. And this is where things begin to get dangerous, because all of us look at graphs to try and figure out where anomalies lie, right? And if we saw two values that appear to converge, we might take action based on that, or lead us down a bad set of conclusions, or at least a bad research process that then wastes our customers' time while we go and try and evaluate things and whatnot. And when in reality, we need to break out of our intuitive perception of this and say, you know what, rationally I'm going to try and keep my look perfectly straight and no, those values have not changed. There's no change going on at 10 a.m. than there was at 2 a.m. that isn't represented, that is unfairly represented, or these two things haven't changed their relationship in any way. Similarly, this can be complex. This is a very old chart. It's imports and exports from 1700 to 1780, right? And if we were trying to make some sort of evaluation or assessment about, net imports or net exports from England, what could we say? Between the period of 1700 and 1720, it looks like imports were going up, but exports were fairly flat, right? So it looks like net imports are increasing. That's fairly easy to read in the first part of the graph. And then right around 1720, exports are increasing, but imports are flat. So it's going the other way. That's great. But now we get to the curvy bit. Yeah, it's always the curvy bits that mess you up. And so, we clearly, sometime around 1765, exports start dropping precipitously. But did anything interesting happen in that gap where things were going up? Well, remember the problem of comparing parallel lines. Those look like they're in sync, but no. The upper line is actually increasing faster than the bottom line in a way that if you compare the differences, there's this huge spike around 1765 of net imports to England, right? And that's, like, you wouldn't even know that there was a completely major event that occurred where those two lines were running parallel to each other. Because again, our brain doesn't notice or think about the verticalness of the difference. It's comparing sideways, right? Your brain likes to go sideways. It's one of its defects. So anyway, when choosing how to graph data, sometimes you need to post-process that data to produce a graph that actually shows interesting things. We'll see another example of that in a little bit. We are 20 minutes. Okay, I think we're probably good on time. All right, graphing the message. Here's a great one. This says population growth, but it's more interesting if you think of it as like, your bank account growth. Yeah, those are like millions, or hundreds of thousands of dollars, right? Okay. When we look at this, we're like, hey, my investments are doing great, right? And I see consistent upward trend, and because it's a compounding thing, it should be getting bigger. The slope should be increasing, right? I don't see any problem with my investments. Your advisor comes, shows you this graph, and says, hey, you're doing great. No need to change anything. I've been rebalancing your portfolio. You're very happy. But you're like, this line's getting awfully vertical and whatnot. And I know that as a human, I can't compare angles, because literally what we're trying to do is compare the slope of that very last segment to the slope of the segment before it, right? And see if the increase in that slope is consistent. So we're doing slope to slope. So we're doing line segments, and what do those last three dots there make? They make an angle, an obtuse angle. And so we're literally trying to compare an obtuse angle to a slightly different obtuse angle to a slightly different obtuse angle and infer things. And we already know humans are terrible at that, so don't do that. Instead, we'll do this. Exact same thing, it's just on a log scale, and it's showing the rate of change. And it turns out that right there around 2000, our investments started doing terribly, well, compared to our previous trajectory, right? But it's only by manipulating data. Like, is it clear that around 2000 something obviously bad happened? There is a little bump, but that might have been just a really good return year. But no, it wasn't just a good return year. It was a fundamental shift in our rate of return. And for the following 10 years, we have been underperforming our previous growth. And that's a huge difference when you're thinking about something like an investment where, oh no, you just did well that year. No, something fundamentally changed. Whatever process, whatever change happened there, it needs to be undone. Think of this as a regression, a performance issue, a throughput analysis of your service. there might be these things hiding in there because you look like, oh, there's just a bump in growth. Like we did really well. Maybe we had a big news event that month, and so we had an increase in traffic, and then everything smoothed out. But no, it turns out we actually have had a change in our customer acquisition, right? You need to be looking deeper into your data than the naive first interpretation. That may not be just an outlier. So that's always fun. Scale matters. Scale always matters, all right? We're all here because we run systems at scale, right? But that's not the scale we're going to talk about. We're talking about the scale on our graphs. Classic example, again, a lot of these come from Cleveland because he was, his work in '68 was a real watershed thing where he really got into this. He was focusing on data scientists and trying to get useful information and communicate data to other scientists. How do you present information so that another scientist can see it, think about it, and then come to their own conclusions and so on. And this is percent composition of elements in meteorites. That's what it is. So we start out here, and it looks like meteorites are mostly oxygen. Well, that's good news. Oxygen's a great thing. And then we got a little bit of iron, and then silicon, and magnesium, and aluminum, and nickel, and calcium, and sodium, and chromium. There's a song in here somewhere, but I'm not that kind of person. If this was a Disney presentation, we would have a lot of fun with it. But once we get down below chromium, like we can say that there's just a crap ton of magnesium compared to aluminum, right? Like at least 5 times. But what is the relationship between chromium and potassium? It looks like there's almost none whatsoever, right? So that's where our good friend the log scale comes in. We're all friends with log scales. Anybody who's doing large systems should be using log scales for their long tails and whatnot. And it turns out that chromium versus potassium, look at that, there's twice as much chromium as potassium. All right, that's like a whole extra chromium for every potassium at no extra charge, all right? And that's not obvious here. I mean, when there's twice as much of something, all right, that's a really big deal. And that's completely hidden in this scale. Now, I don't think I need to go too much further into the benefit of log scales, but this is an example of, by using an appropriate scale, you can draw inferences about one thing versus another. Now, it appears twice as much on this visual representation, but remember, there's a log scale. It's actually more than twice as much just because it's twice as far right on the chart. So it's actually an even bigger difference than what it intuitively feels like. Fun stuff. Now, it helps that this is sorted. This is another minor detail of when you're going to plot a bunch of data, sorting it allows you to make much easier comparisons between aluminum and nickel. Now, if aluminum were all the way at the top of the chart and nickel were all the way at the bottom of the chart, and we were trying to figure out, are they the same? Are they different? That gets back into the ability to compare small differences in large values. And so when you're doing charting like this, you want to be sorting on some ascending or descending values so people can make adjacency comparisons. This does make life harder if instead people are like, oh, I want it sorted alphabetically so I can quickly find where aluminum is because it'll be at the top of the list, right? But when it comes to data presentation, humans are okay with scanning a list of things looking for a single item because actually you can, when it comes to looking for words in lists, your pre-attentive and iconic memory actually knows what an A looks like, and you go, okay, there's an A word, it's aluminum, right? So this is where you would actually say it's better to sort it by something that allows for comparisons between iron and silicon directly as opposed to someone I'm going to go and look up what the values were and then do an absolute comparison, because you actually get multiple readings from this graph, but you don't lose the ability to say, how much cobalt is there? All the way at the bottom, but I found it, right? So, fun stuff. This is another great example of long tail and log scale. You'll have to take my word for it that the area under this curve is 1. It represents the distribution of purchases at a hypothetical store. And as with most online shopping, clearly there is a big spike in low dollar purchases. That's where there's a crap ton of money. And then there's this long tail that goes out to $10,000 purchases, right? But as soon as we apply log scales to the horizontal axis, we discover a really interesting property. Our customers are basically bimodal. Turns out that, yeah, there's a peak right around $60. That's the typical purchase. That's the mode for the low end of purchases, right? But look at that, right around $3,000, we have a lot of shoppers that do that. That's a whole separate opportunity for merchandising and for figuring out what your customer behavior is. And if you were only looking at a typical long tail graph of customer behavior, is it obvious that there is a huge bonanza of activity at 3,000? There is a bump there, right? There's a bump there at 3,000, there's a bump there around 3,800 and so on. But it's not as blatantly obvious as applying the right scale and looking at the data and that's pretty impressive how many customers are giving us money at the $3,000 range. There might be something to that. Now, this is of course money, but imagine this is distribution of latencies of your requests. then all of a sudden it becomes really relevant, doesn't it? If I saw this as my latency graph, I'd be like, hey, it looks like we're doing pretty good. Most of them are coming in a few milliseconds or whatever. But if I saw this, I'd want to have a sit down in a conversation with someone and say, what's happening at 3,000 milliseconds? There's a story there. We need to figure out what that is. So, scale matters. High density plots. Oh, I just came to the first thing that I realized I've shorted you on and I left out. Binning isn't in here. Okay, I'm sorry. Well, we only got 12 minutes left, so it'll be okay, because we wouldn't be able to fit it anyway. Scatter plots are great. Binning is a much better thing. You all experienced binning when you do heat maps, right? And we're all familiar with rectangular heat maps. There's another thing called hexagonal heat maps, which are a lot of fun, where it's better for pure two-dimensional data than something like rows of servers and data centers, which are very rectangular, unless you have hexagonal servers. I don't think anyone has hexagonal servers, but in fact, there might be a startup idea in there. Make hexagonal servers to increase density because you can fit more, because you'd be zigzagging your rows. All right, my idea. No one take it. But I am looking for investors, angel investors, and partners. What's that? The old thinking machines? Well, they were round and they just didn't stack anywhere, and there's like those little like onyxes and whatnot, and these like you couldn't even put like a pizza box on top of it. Anyway, yeah. Oh God. Okay. Focus. All right. So here we have got it's a distribution of something or another, like how many times someone said this was their favorite thing or whatever. It's from Robbins. It's a graph. But the thing is, where things like bunch up, it can be hard to see the detail of what's going on. And so that's where something like jitter comes in. You're literally just applying a randomizing element to your plot to make a better visualization, right? And so this can be a very useful thing when you have graphs where, like, I can't really tell you anything about the low end of just about every single one of those. I do know that, okay, it looks like families and next stop Worcestershire are way out there as the high popular end, but I can't really say anything meaningful about that. When I do this, I can begin to find things like, oh, look at that, there's a lot of clustering at the low end of families. There's a lot of clustering at the low end of the universes in your hands, but it tails off much more quickly than families does. And so on and so forth. I mean, so by adding some jitter to your representation, you can retain very simplistic plots, but you get more information out of it and allows more deeper readings. Binning, I bet this has no slides in it. Yep, there you go. That's the part that I forgot to do. All right, aspects in banking. All right, 10 minutes left. Okay. Banking, this is a concept called banking to the 45. Has anyone ever encountered banking to the 45? Oh, wonderful, a new topic. All right. If you've done a lot of R work, you might have found that some of the plots allow you to say, oh, please bank this to the 45. So when we look at these two graphs here, they are basically the same graph, but because of the really screwed up scale units, it makes it hard to see what's going on with this value. Obviously, the angle changes. But again, we're bad at obtuse angles and we're bad at comparing it. Now, I only have 3 data points here, but imagine this is in the middle of a much bigger chart and you're trying to compare this section of the chart to another section of the chart. This is a very bad way of presenting data. Banking to the 45 is a methodology where the sum of the slopes, the average of the slopes of all line segments in the graph should be 45. The net effect is something that looks like the upper left-hand corner here, where generally the data starts at the bottom left and goes to the upper right, and you use the full expressive range, okay? And that can be a very beneficial thing because it allows people to read data and you're actually taking advantage of all that real estate that you're using. All right, but it's not just about the real estate, it's about the aspect ratio as well, and we'll see that in an example after next. But it also can be used to great effect to influence people. There's 2 real big groups of research when it comes to data visualization. There are those who believe that visualization is a tool of rhetoric, and you should be used to convince people things, and it's fair to manipulate the use of your data presentation to achieve a particular end. And there are those who think it's a tool of communication where it's about accurate and expressive representation of the underlying truths inside the data. The 2 don't really come to blows very much because they're data scientists and researchers and they don't really do that thing, but it's 2 very different schools of thoughts. And like if you see infographics in a newspaper, that's very much a rhetorical kind of graph. In fact, I've got about 20 in my rogues gallery of really bad graphics, and I think half of them come from news media. So anyway, Tilting to 45 is basically using the entire expressive range that you have so that someone can see the detail of your data. That's the same data plotted 3 different ways. Here's an example from Huff. He's the one who wrote How to Lie with Statistics back in the 50s. If you haven't read that, it's a very thin book. He basically talks about how to manipulate the presentation of data so it's honest, but people draw different conclusions. This is one of his classic examples. On the left, government payrolls are spiking through the roof. And on the right, government payrolls aren't doing anything, right? And this is back in the 50s, and so $20 million was the government payroll. And so this is an example on the left, one could say is more fairly banked to the 45 because it's using the full range, but he's also using something called a hidden baseline where the 0 of the scale is way off the bottom of the screen. But if you don't use a hidden baseline, it can be very difficult to bank to the 45 and you don't get to see the actual dynamism in the data, right? Anyone who's ever looked at a chart where it's basically right up at the top, there's a bunch of squiggly lines, and you don't really know what's going on, and if your tool doesn't let you eliminate that and set the starting point much higher, you don't get to see the variation of the data. That's a problem. But here's the opposite example. So this is the number of observed sunspots per year over the course of, looks like 200 years, yeah, 200 years or so. And it's like, okay, look at that. The sunspots go up and down, up and down, up and down, right? But mathematically, now your graphing tools often have the option to calculate the bank to the 45 representation of the data. So because this isn't banked to the 45, there's less visual information than we could otherwise get out of this. The next slide is an automated banking to the 45. Now notice how the aspect ratio gets completely smashed, right? And this might actually even feel like, is this a better graph than this one? Right? Now this is where judgment comes into play because it's not always obvious as to which graph is better. But there is one very interesting thing you can tell on this graph, which is extremely hard to tell on the other graph. And that is that when a sunspot cycle begins, the ramp up in sunspots is much more rapid than the slow decline at the end of the sunspot cycle. See how the slope on the line on each uptick is steeper than the declining slope of each? And that's something that when you look at this, it wouldn't even occur to me to examine those slopes because they all look exactly the same. And it's only by using the math to find the average slope of each segment and compute an appropriate aspect ratio that allows those to average out to 45 degrees that do we see that, look, there's something meaningful going on there. There's probably something meaningful going on in your server data that you can't see just because of the aspect ratio in which you're presenting it to yourself or to other people. Burton efficiency. I put this up here because I actually listed it in the description of the course. It's way too big. And it is a completely different school of thought than Cleveland and Tufte. And he was a cartographer, not a data scientist. And so I decided, it seemed like he had some ideas that seemed like it'd be cool to talk about of, how many readings of a graph can you get out of one plot? So the more readings are the better. But essentially it's like the more ways you can read a graph, that's usually better. So we'll just use that as a summary of Burton efficiency. But his taxonomy is really designed around things like how to put cities and populations on maps and whatnot, which is not of interest to most people. So awesome. All right, we have 4 minutes left. I've got a few examples of really, really terrible graphs. I hate pie charts. For the reasons described in the section on acute and obtuse angles, pie charts are the devil. They are the worst possible plot. In fact, even Tufte and Cleveland, you'll go find these just academically acerbic quotes, things. Yeah, they say things like, while they have their place, for almost every possible instance, there is a better chart type available. I mean, these very academic insults of pie charts are in there. And they're right, because if you look at a pie chart, how can you read it? You could look at the length of that curved arc on the outside, right? But we're terrible at reading curved distance. Instead, each of us takes the chord point to point and is comparing that. But that's not the right thing, especially once you go beyond 180 degrees. The chord is now smaller than the actual arc, right? And so you get this error built in, and it's terrible. The only redeeming aspect of pie charts is that if you're willing to put up with the error in acute angle comparison, like the orange and the brown here, if it weren't labeled, they would look almost identical. In fact, one is 50% larger than the other, right? As a representation of the sample size. But you can, at the very center, look and, okay, blue is clearly much bigger if you look at where they meet in the center, right? So you can just a little bit read this, right? But then, of course, some genius decided to invent this, which literally removes the one and only bad saving grace of pie charts. Yeah, anytime I see this, I just want to grab a book and beat someone to death with it, right? I have burning hatred of 1,000 suns for donut charts, which are so much worse than the worst chart out there, which is pie charts. And of course, when it comes to pie charts, you do not have to look far for just horrible representations of pie charts, where things are this is useless to me. I'd rather have just a table of data, right? This is the only acceptable pie chart in the world. This is allowed. You have my permission to use this on any dashboard, right? In fact, I think it should be a standard widget on any piece of dashboard software, just, you know. And then I've got others that, I mean, when it comes to pie charts, the world just gets worse and worse and worse. I mean, yeah, it's like, what were you thinking, you know? How many times did you get hit in the head, you know, before you began this project? This has no readings whatsoever. I cannot untangle this graph for the life of me. I can even tell if the right side is meant to be the left half of that other chart, or they're two separate charts that are only 180-degree pie charts. Oh, and of course, notice how it's a little tiny donut. They don't have anything right at the center. Anyway, so I've got a few others. Do we have questions? Does anyone want to ask any questions? We only have a minute and a half left, or I can flip through the remaining 10 bad examples. Yeah.
Yeah. One quick question. Do you think that if you're presenting data visualization to a certain type of group, that you should cater it based on how they actually consume the data?
Yeah, absolutely. Some groups, like if you're presenting data to your CFO, they're probably going to be very happy without a graph and just a chart showing numbers in a giant spreadsheet dump, because that's how they're used to interacting with data. If you're showing it to someone with an MBA, you know, crayons and butcher paper is probably the right way to do it. So yeah, you definitely want to consider audience. There's actually a few good books that I don't have in my notes that are specifically about communicating with data. There's a great one that I just got that I meant to use as a resource for this, but since it weighs like 40 pounds and it's like a $90 like coffee table book on data visualization, I didn't decide to haul it back and forth from home to work to put this stuff together. But it's a great book that has a lot of great resources on, you know, knowing your audience, selecting the data that's appropriate, and formatting it in a way that they expect to consume it. And that's basic communication theory of understanding how the recipient of communication wants to receive data. What's that? I will tweet it out later. It's a long title and I forget. I think it's Few, F-E-W. I think Edward Few, Alan Few, F-E-W is the name. Anyone? Dangers of averages. Well, you throw away a lot of data when you take an average. I've got 15 seconds left, and the next speaker. Who's the next speaker? I'm stomping all over your time. You sure? All right, you're the one who's in charge of when I stop. 5 minutes? All right, I've got 5 minutes from the gentleman in the front. Averaging data is always very dangerous because it's from the family of what's called descriptive statistics. You know, they're much better statisticians in the audience than I am. But essentially, it only presents one particular aspect of the data, and it's a single-dimensional one. Now, plotting averages can be even more. Thank you. Can be even more complicated, but. Averages are dangerous business, you know, because most importantly, because you throw out the outliers, or if you have, God forbid, you have a bimodal distribution, it completely ignores it, and if you're making actionable decisions based on that, then you're going to end up doing all sorts of bad things. There's such a thing as too much information. We got. Again, now this is great because it's a 3D pie chart. Ooh, let's create perspective, which makes it even harder to compare things because the things at the back, have they been visually foreshortened or not? I don't know. Hopefully I'm not making an important decision. Now this one actually, there's so many labels, but notice that not all those colors appear on the graph. It's like, what was this person thinking, you know? It's like they cut and paste from the atomic table and then just added 4 numbers. Anyway. This is a great one. Okay, now it was very hard finding examples because we just came out of a very interesting political cycle, and most bad media infographics are related to politics. Now this is a fascinating one because it's from before the election, but it says Project Fear hit trust in government, and I'm not sure how to parse that. Does that mean that government has a project called Project Fear? Right? What is it? Oh, what is it? Oh, awesome, awesome. Because they were using a fear-based, got it. So this is from the Brexit. Okay, that makes sense because there's the Union flag and the EU flag there. Yeah, that's iconic memory kicking in, right? But what's interesting is in British politics, are red and blue used to denote conservative and liberal? Red's left wing, blue's right wing. Because interestingly, even though we're showing date from 2015 to 2016, and the percentages are changing, and the hidden baseline make it look like it's huge, it's a 3% change, which in politics is a large number. But they're also relying upon iconic memory to give you an emotional response to the big number is somehow a left-wing number, and the right number is a right-wing number, but these are dates in time, right? It's not like this is party A on the left, party B on the right. This is a year ago and today. Right? But they're using color and iconic memory to trigger a response. And if you start looking out for that, you'll see that often color will be used to say, oh, not only do we have an effect, we're going to use color to imply cause to that effect in a very subtle manner. All right? Did they double the numbers? What? Oh, yeah, that is tricky. Nice. Yeah, all right. So anyway, if you want bad graphs, look at anything political or anything news. All right, I got 1 minute left. This is also another just terrible graph. They're using icons, but never use icons to represent data points. It's like, okay, the plane's on the upper right and the upper left, but what does that really mean? You basically have to fully engage type 2 thinking to decode this graph. And if you're going to do that, you may as well give someone a table with what, 1, 2, 3, like 15 numbers in it. If you're going to require that much thinking, don't even use a graph. This is great because this uses pre-attentive cognition to sort these and group them. But interestingly, because of the USA Today logo, our pre-attentive cognition identifies USA Today as a planet. Because our pre-attentive mind says, oh, planets are round. Oh, look, there's a fourth planet. I didn't know they had their own planet. So, fun stuff. And of course, the graph is like, scientists estimate the planet measures somewhere between the size of Earth and that of Neptune. So they literally just made a circle that was halfway between the size of Earth and halfway. So the graph actually has no meaning whatsoever. It just says, this is between that and that. What? Yeah, danger of averages. There you go. They average the size of Planet 9 right there. And then these are just mislabeled things, like 13% is huge and 34%. It's like, yeah, it's bad. This makes no sense. This is a textbook. Who has the world's strongest economy? And the vertical bars are United States and China, but they're broken. Now, United States has both a United States bar and a China bar, and China has a United States bar and a China bar. It's just, yeah, it makes no sense, even if there was. Now, this is, oh, I love this. Have a look at the red line. It goes left! Yeah, okay, I got 8 seconds, I'm done. There's tons of, all right, that's it. All right. Thank you very much, everybody, and I apologize for going long.